Hey, welcome back. Thanks for showing back up again. We're going to keep rolling through our hydraulic fundamentals. One of the things that I forgot to mention in our previous segment was we talked about flow meters, okay? Well, one of the things I forgot to mention was the symbol, which is going to be important to know, okay? This is the symbol for a flow meter that you would see in a schematic, okay? It sort of looks like a tennis ball, in my opinion, and that's the way I always remember it. But that flow meter looks a little like a tennis ball, flows through there, and it gives us our flow rate in gallons per minute. It could also be in liters per minute, but in our class and in the U.S., we typically will use gallons per minute. But I forgot to show you that to you, so I just wanted to bring it up to you, okay? So we left off with, what if we want to control our flow, all right? Well, there are some advantages to doing that, okay? We can control the speed at which our actuators move, such as cylinders stroking or returning or retracting. Also, the speed of a hydraulic motor can be controlled with a flow control valve. And you can also use it to, if you're trying to extend a cylinder with a certain amount of precision to get it right in the right place. If it's pushing something out there at a certain position and it needs to go slower so it doesn't bypass maybe a limit switch or something too quickly, you can control the flow of that and precisely control its positioning as well. Now, there's a problem with this. We don't ever want to generate heat. But in this case, this is one of the devices that will generate some heat, but it helps us in our process. Now, heat generated in too tight of bends in the hoses and a lot of bends and 90s in our pipes and things like that create and generate heat unnecessarily. We don't get anything out of it. In this case, we inherently build a little bit of a resistance and heat in our system through a control valve, flow control valve. But it's for good reason, okay? So let's get into this a little bit on how this thing works. This is the symbol for a flow control valve, and you're going to want to know it. This little arrow right here tells us that it is adjustable, that we can vary the flow. It's not a fixed amount of flow going through. We can vary the flow of the fluid going through the flow control valve, okay? Now, the flow control valve usually has an integral check valve built into it, and this is the check valve right here, all right? And what it does is it controls the direction of the flow, not the rate, but the direction of the flow. And here's how this works. This is a check valve, and if we had oil, say coming from our pump and our valve and things like that, and it's coming through our system this way, all right? What it's going to do is there's a little spring back here, typically, and the oil pressure, the flow of the oil will come and lift this off of its seat, and the oil will flow around it and on down our path. Okay, that's how that works. Now, if we have oil going this way, what it does is it gets back behind this ball, and this could be a ball, it could be a pintle sitting in a seat or whatever, but they use this as a symbol. And what this does is the oil will get behind here and further seat it into the ball into the seat and block the flow of oil going this way. Now like I said, we'll come this way and off-seat it, and it will allow to flow. But when we push oil this way in this direction, it will only let it go so far, seats it, and it blocks it completely. Okay, nothing can flow around it. All right. So that is what a check valve does. And again, the flow control valve has a check valve integral to it, or built into it. It's integral to the valve. And this is a symbol that you are going to want to know, okay? I bet you're going to see it a little bit later. There's a big hint for you, okay? So, like I said, the check valve controls the direction, but not the flow. And this is how this works. It basically makes the fluid flow through the metering section of our flow control valve, and we control the flow rate, or the GPMs, that we're allowing to pass through the flow control valve. Breaking it down a little bit more for you, okay? Here's how it works. You got a pump, and we're going through our valve, and we've got fluid flow coming through this way, all right? Now, as we said earlier, fluid is going to look for the path of least resistance, okay? I wasn't just making that up. Here's where it comes into application. All right, you got a couple of parallel circuits here. The oil can go one of two ways. All right, so we got oil flowing in here, and this is our metered section. Now, this one doesn't show the adjustment. I meant to show you this earlier too. Here's a little flow control valve. It's got a little adjustment. That little arrow that I was showing you earlier, that's basically the symbol for this adjustment knob. And what it does is it throttles the amount of flow down, or we can increase it by lifting the valve off of its seat in this area right here, okay? But we got oil flowing through here, and we're kind of restricted here. We've got some that allow it to flow, but it's kind of restricted. So the oil is naturally going to look for its path of least resistance. So it's going to want to go through here. And remember, we said they've got a little spring back here, just a little one, and the oil will pull this ball off its seat, flow around it, and then it will come back on the cap side of the piston on this cylinder, and it will extend the cylinder, okay? And we really won't have any control over our flow, because this is the path of least resistance. There's no control. There's no metering through this. Our metering is done right here. This is the most resistance, so it's going to go through here and just go full flow into the backside of our cylinder, okay? That's with the fluid flowing in this direction going into the valve. But if we put that same valve on the exit side of this for the fluid on this cylinder, and we have our oil flowing through here, okay, we're pushing our cylinder this way, all the oil on this side of the piston is trying to evacuate, and we are forcing it into our flow control valve. Now, the oil can go one of two places, just like we showed you earlier, all right? However, when it chooses to go this way, it's back behind that ball, and we're just further seating that ball into its seat. So it's fully blocking it, and it's forcing all of the oil to go through our metering section so that we can have full control of the flow, okay? We don't want partial control. We want all the flow to go right through here. So again, we're forcing the oil up to this point. It says, hey, you're not going anywhere. I'm blocking you off. You're going to have to find somewhere else to go. So it does, and it goes through this metering section where we can control the flow with the GPM going out to our tank, okay? So we are actually controlling the flow and the extension of this cylinder by controlling the outflow of fluid through our flow control valve. So that's how that works. And here's what it looks like in a schematic. Again, we're looking at symbols that you should be getting more and more familiar with. Look at here, we got a fluid conditioning device. I know that's a filter because I've got dashed lines in my diamond shape, okay? Diamond's fluid conditioning. These dashed lines tell me it's a filter. So we're going to filter that before it goes to our pump. That's creating pressure that we can read on our gauge, going to a directional valve. And I will cover directional valves a little bit later so that you understand the operation of that. But this is a directional valve, and again, flow control valve going into our cylinder. So we got pump pressure, or pump flow, going into this side of our piston. It's pushing and wanting to extend the cylinder. The oil here has to go somewhere, so we're forcing it into here, into our flow control valve. It's got one of two paths it can take, okay? You go to here, and all it's doing is seating that valve in there tighter, so it's saying, you can't go through here, you're going to find another place to go. So we force it through our adjustable, see the arrow, our adjustable passage through or orifice through the control valve, and we can adjust it and throttle it down. We could even close that or throttle it down enough to where we can make the cylinder stall while it's trying to extend, okay? We don't necessarily want to do that, but we can control the speed by controlling the outflow of this oil, and then of course it'll go back to tank. Now, if we shift our valve to where the oil then ports out of port B, okay, we're going through here, and remember, we kind of choke this down to slow it down while it extends. Well, that's our point of resistance right there, path of most resistance, so we're going to look for the path of least. It's going to come in here, pull that ball off its seat, full flow of oil, and we will retract that cylinder with full flow because there's nothing restricting it going back into our valve, into our tank. So it's going to come back at full flow. So we are metering and controlling the speed on the extension side, and when we retract at full speed, okay? Full flow, all right? That's the schematic in a diagram. Again, it gives us the control over our actuator, and it allows us, and if we know what our speed is based on our flow meter, we know what our flow in gallons per minute based on our flow meter, we can then calculate how fast that rod is going to either extend or retract. And we got a formula for that. But I'm going to make life a little bit easier for you this time around, okay? Our formula for determining the rod speed's extension rate or the rate at which it retracts is flow rate over area, or flow rate divided by area, okay? Now, we have to first convert our flow rate, our GPM, from our pump. We have to convert that so that it can be compatible with dividing it by its area, okay? You can't divide gallons per minute by area, okay? So what we have to do is we multiply this by 231. The magic behind 231 is that that is the displacement of 1 gallon of water, okay? 231 cubic inches, okay? So we multiply whatever our pump flow is. I think I showed you one at 5 gallons per minute. It can be 1 gallon per minute, whatever that flow rate is. We multiply it by 231, and then we divide it by our area. Now, speaking of area, this is where it gets a little bit easier for you, okay? We used to, previously we have been calculating area by taking the radius, squaring it, and multiplying it by pi, 3.14. All right, that was so that we could find, I wanted you to get familiar with the radius and then how it was relative to the diameter of that cylinder. We understand that now, okay? From here on out, for the rest of this class, we can use our area formula of D, which is our diameter of our cylinder, square that, and multiply that by 0.7854. 7854, I think we talked about this in a previous example, is that if I had a square and I put a circle in it, that circle would take up 78.54% of that square. Everything on the outside edges there would be, I guess, waste you could consider. But in order to find the area for what we're looking at now, we simply square the diameter of our cylinder, whether it's 6 inches, 4 inches, 3 inches, 2.5, doesn't matter, square that and multiply that by 0.7854. And that will give you the area of our piston, okay, or cylinder, same thing, okay? So example, we got 3-inch cylinder, so we take 3 squared. Remember, 3 is not multiplied 3 by 2, it's 3 by itself, so it's 3 times 3. We multiply that by 0.7854, and 3 squared, 3 times 3 is 9 times 0.7854, and you come up with 7.07 square inches for a 3-inch diameter cylinder, okay? So that's the new way I want you to start using this to determine your area. It'll make things easier for you too, okay? So what we're trying to do now is calculate the rod speed, all right? Again, our formula is flow in GPM times 231, and then we will divide that by our area, and that will give us the rod speed in inches per minute. All right, let's see how this flows. All right, so we got a 3-inch cylinder, and we've got a pump that puts out a maximum of 1 gallon per minute. All right, so let's do our math on this real quick. Okay, so we have an area of 3 squared, our diameter squared, times 0.7854. As we showed earlier, is 7.07 square inches for that 3-inch diameter cylinder. Our flow rate is 1 gallon per minute, 1 GPM times 231, pretty easy. We have a 231 for our flow rate, 231 gallons per minute on our for our flow rate. That's our converted number, I should say. So we take our 231 and divide it by 7.07. I think I got on the next slide. Yeah, 231 divided by 7.07. Our cylinder rod speed for extension is going to be 32.67 inches per minute. Okay, that's the rate at which it will extend based on the flow rate of 1 gallon per minute and the fact that we have got a 3-inch diameter cylinder which has a 7.07 square inch surface for its piston. Okay, those are the two factors that determine our rod speed. So let's do another one real quick, okay? A lot to take in, and I'm here to help you if you've got any help. Also, your lab instructors, they will also help you with this too. They're very proficient at it. But let's take another example. Again, here's our formulas, all right? And again, this is the new way we're going to calculate our surface area of our piston. So this time, we're going to take a 4-inch cylinder, and we're going to square that. 4 times 4 is 16, and we're going to multiply that by 0.7854. And that will give us a surface area of the piston of 12.57 square inches. Okay, so we got our area, all right? Now, we also said that we're still going to use a 1 gallon per minute pump. So we said 1 gallon per minute flow rate of the pump times 231, okay? And we come up with 231, and we're going to divide that 231 by 12.57. I think I got it on the next slide. And we take 231 divided by 12.57, and we wind up with 18 inches per minute extension speed. So our cylinder will extend 18.38 inches per minute. So that is how we calculate rod speed based on a couple of things. Flow, okay, you can find the flow rate with our flow meter, okay, and also the surface area of the piston. And we found a new way to determine that by simply squaring the diameter and multiplying it by 0.7854. So that's going to take care of this segment right here. So I'm trying to show you how these formulas are actually applied in the fluid power. You know, we're talking about flow rates and we're talking about surface area. There's a reason we had to learn all this stuff in the first lesson, and we practiced it in the second lesson, saw it a little bit more applicable. Now we're seeing it really come into play because of its functionality. So we can now determine how fast a cylinder will extend based on how big the cylinder is and how much flow our pump's putting out. So that's why we're learning these formulas, and I'm not just teaching you formulas for the sake of formulas. I promised you I wouldn't do that. So anyway, that's what we got for this segment. We're going to have some more, so make sure you come back and, again, get hold of me if you don't understand anything, and I'll work with you. So other than that, let's shut this one down and be sure to join me for the next one. Thank you.